Okay, yeah. So our next presenter is Alyssa Yasuhara, and she belongs to Newton High School in Newton, Massachusetts. Yeah. So here is Alyssa. Okay.
Okay, thank you. Can everybody see my presentation?
Yes, I can see it. Yeah.
Okay, thank you. Thank you for the introduction. My name is Alyssa Yasuhara, and I'm a 10th grader at Newton North High School. And I'm so honored to present today at ACID's conference. So thank you so much for giving me the opportunity to present. My project is about an Arduino-powered navigation device for the visually impaired. And this was originally a group project, but because of schedule conflicts, I'll be presenting on behalf of my team. Imagine walking through a crowded street without being able to see people, objects, or changes in your environment. This is exactly what 7 million people in the United States face with visual impairments, including macular degeneration, cataracts, diabetic retinopathies, and glaucomas. And many of these people rely on adaptive technologies to help them navigate through their daily environments. These are just some examples that I found on the market that are available to people with visual impairments to help them with navigation. For example, we have here the smart cane on the very left, and in the middle, smartwatch and smart glasses with a camera. And all of these include cameras and sensors. However, there are a couple problems with these products. First of all, a lot of them are extremely expensive and not really affordable for people. For example, commercially, when these smart canes, smart bands, and smart glasses are sold, they're often hundreds of dollars. Second, they're also inconvenient and uncomfortable. For example, these glasses require you to have them on all day without being able to take them off. And third, there is no above the waist detection for some of these devices. For example, this wristwatch and this cane, which only detects objects below your waist. So, to solve this problem, I consulted with a member of the visually impaired community, Louis Doe, who works with the Carroll Center for the Blind. He helped us identify the key aspects to focus on and integrate into our project. And these are the three most important and key things that he highlighted. So, first was for the device to be comfortable to wear and not too big, as well as for it to not require any unnecessary movements. For example, he had experience with the Sunu smartwatch, which required him to hold his arm out for the entirety of when he was wearing it, which was really uncomfortable for him. And third, he wanted above the waist detection to help him detect objects like tree limbs or doorways that he often bumped into. So, this was our take on the development of our project. We went through a couple of stages of iterations and designs. As you can see here in the first prototype, we used an Arduino Nano and a breadboard, as well as a couple jumper wires. And throughout our different iterations, we tested and prototyped. As you can see here in the third prototype, we integrated an ultrasonic sensor. But because we found that time of flight sensor, which is an infrared sensor, is a lot quicker with sending data and retrieving data with distances between objects, we switched from an ultrasonic sensor to a time of flight infrared sensor. And then we also started to use an ESP32, which also had built-in Bluetooth communication. And this was what our final prototype looks like. So we call this a brooch sensor because you're able to attach this device onto any part of your clothing because it has a pin on the back. So we integrated this name into it because we thought it was similar to a brooch where you can attach it into your chest area. The second part of our device is this wristwatch buzzer, which attaches onto your wrist with a Velcro strap. So in our first couple of prototypes, we used, as you can see circled here in the red, we used a buzzer or vibration buzzer, which is wrapped in aluminum foil. And then throughout our different prototypes, we also integrated pill caps. And in our last iteration and prototype, we 3D designed and printed a case for all of our components to fit into, as you can see here at the bottom. So here was kind of a rough timeline of how we built this project. This extended over a period of 8 weeks. And as you can see here, in our first couple of weeks, we started designing and meeting with different clients to have an idea of what our project would be focused on. In weeks 3, 4, and 5, we kept prototyping and iterating and replacing different components. 6 to 7, we presented this prototype to our clients, the Carroll Center for the Blind. In week 8, we also kept developing this and integrated different components such as the ESP32 and CADing our case. So here are the different components that we use in our project. So to list some of them out, the ESP32, which I mentioned, the VL53L1X time of flight Arduino sensor, which is the infrared sensor. We also use rechargeable batteries, an antenna for the Bluetooth connection, a haptic buzzer for our wristwatch buzzer and Velcro strap, as well as 3D printer and the filament for the case, solder board, and a couple of switches. So here's what the final prototype of our device looks like. First, on the left, you see here is our brooch-like device, which is attachable to your clothes. And on the right here, which is our wristwatch with the haptic feedback. So the way that this device works is first, the brooch-like sensor device reads distance away from an object and an obstacle from the person. Then the sensor connected to this ESP32 sends distance data to the buzzer, which is connected to the ESP32 on the other end, and they communicate. And the buzzer ESP32 converts this distance data into frequency of buzzes. So as the person approaches the object, the buzzes become more frequent and faster. And as this user becomes farther from the object, the distance becomes larger, and thus the buzzes become less frequent. So these kind of buzzes allow for the user to feel the haptic feedback, and it kind of indicates the urgency for the user to move away from this object. So to highlight the main components of this project again, which is first the above the waist detection, we're able to connect this device on anywhere above your waist, around your chest area preferably, and it has a 27-degree field of view as well as a 4-meter distance range, meaning that it is able to have a really wide range of view of objects. Second, our device is really lightweight and comfortable. So together, the two devices weigh less than 100 grams, which is a lot more light than competitive devices on the market. It's also comfortable because the user doesn't have to do any extra work for this device to work, as it is connected to the user and moves with the user as the user walks towards the object. And lastly, this device is cost effective. All of the components combined cost less than $50, which is a lot more affordable than the competitive prices that you've seen before, which I showed you, which were hundreds of dollars and if not thousands. And here's the code that we wrote in C++. And this is just some of the members that we presented to at the Carroll Center. They were able to test out our device and give us valuable feedback. And we hope that this device will give them a more improved sense of navigation and tasks in their daily lives. And these are some of the credits and references that I have. And I want to give a special thanks to the American Society of Science, Engineering, and Technology, or ASSET for short, the organizers and committee, for giving me this wonderful opportunity to present my project and presentation today, as well as the Lagerbouts Foundation and everyone else who have supported me throughout this project. Thank you so much for listening and for your time, and I'm open to any questions that you have.
Okay, no
So,
problem. Go
hi,
ahead.
Alyssa. How far
Hi.
you are to bring this your thing to the market, or just to be more, to bring in the market? So how close you are, or did you
This is
compare? Yeah.
Yeah, thank you for your question. So
Mhm.
this project we hope to bring to the market soon, but we have to
Mhm.
go through a couple more iterations of prototyping, as well
Right.
as improvements in the code.
Right.
And we actually have talked to the people from the Carroll Center to receive feedback from them. So we plan on going back there once we have done our final prototyping, but this is
Yeah.
still in progress, and we hope to extend this project in the future. And I hope that, yeah, like one day we'll able to put this on the market for people to utilize and put to greater use.
Do you have any competitive product in the market till now, or you will be the first one to introduce this to the market?
I think there are already existing devices on the market,
Okay. Yeah.
but for us, like we have thought of this idea ourselves, and I'm not sure if there are any similar
Mhm.
ones. But as I presented before, there are devices that already exist on the market. However, this market is really limited, and there aren't
Right.
many choices for these kinds of people to access this kind of devices, especially because they're
Right.
expensive or they don't have the specific needs of the visually impaired. So one of the
Right.
things that we wanted to focus on was the specific needs that these people with the visual impairments had. So before creating our device, we actually interviewed a couple of the people from the Carroll Center, as well as one of the
Mhm.
workers who is also part of the visually impaired community. And we kind of interviewed them on what they thought about these devices on the market and what they really needed. And we tried to integrate those specific needs of those people into creating our device.
Okay. Yeah. Good. Yeah. Good
Thank
luck
you
with your, yeah.
Yeah, so
Bye.
Alyssa, it's nice presentation.
so much.
Yeah. Yeah. So